let's start our job to calculate internal forces with the given beam problem. And finally, after we calculate the internal forces at everywhere, we need to plot. And don't forget, finally, we need to plot the moment and the shear diagrams, because they are not constant in general. That's why you have to use a figure to see where you have the shear force and the bending moment. You cannot just use a number. Okay, so let's take a look about this first example. That's simple enough. With this given beam problem, at point B, there is a pin support. At point D, there is a roller. In addition, there are two applied concentrated load acting on point A and point C respectively. Now, we need to draw, or we need to plot the shear force diagram and the bending moment diagram for the entire beam. Okay, so for chapter 7, there's always the same question. The question is, you need to plot the shear diagram and the moment diagram. But I don't want you to finally just plot something like this directly without showing me the reasons. So we need to follow the steps in order to finally end up with what we call the shear and the moment diagrams. Okay, so I'm going to switch this one back to my overhead projector to show you step by step using method 2. And that's a unified, universal method for solving all beam problems. So that's why I want to talk about that method. The first method, the text briefly mentioned that, have a lot of limitations. And basically, they just kind of using some kind of imagination for plotting simple beam problem. That's why I don't want to talk about that. Okay. However, for any given beam problem, the first step, just like the first step for solving truss problem, is to calculate the reactions. As always, the first step. Okay. So let me switch back to the document camera. Okay, so let's look at this example. That's the same thing I just copied from my slides. We need to calculate the shear diagram, the moment diagram with this given beam problem, right? So first of all, first step, we need to plot the entire beam free body diagram to calculate the reactions. That's typically always a first step for solving beam problems. Okay, so first of all, I need to plot or create the free body diagram. So by looking at the entire beam, that's my rigid body. This is point A, this is point D. For this rigid body, at point A, there is a force, which is 20 kilonewton. And at point C, there's another force, which is a 40 kilonewton. Okay, so these are the two applied forces. In addition, point B is a pin support. So that means I need to cut point B here so that I need to give two reactions. And I call this the BY and then BX. Okay, there's a pin. At point D is a roller. So if point D is a roller, then I cut point D. Correspondingly, I need to give a force. It's called dy. Okay, so you should be very familiar so far, right? Because these are the typical chapter 4 steps. Okay, with this free body diagram, we can easily write down the three equations, because that's a two-dimensional free body diagram. By collecting all the forces in x direction, z equals 0. All the forces in x direction, that's bx. And that's equals 0. That's simple enough. Now, we need to collect all forces in y direction. So now, let's see. You have a by going up. You have dy going up. you have 20 kilonewton going down, you have 40 kilonewton going down, and that's equal to 0. And that's the second equation. Number 3, the equation is take a moment at a certain point, and static equals 0. So we have a lot of points to choose, right? We have point A, point B, point C, point D. So typically we choose a point with more unknown forces involved. So you can pick point B, or if you like, you can pick point D. It doesn't matter. So point B and point D are better than picking point A or point C. Okay? So let's take the moment at point B. So when we take a moment at point B, now let's just collect all the moment due to forces. First of all, we have a force 20 kilonewton acting at point A. What's the moment of this 20 kilonewton at point B? So that's the 20, which is the magnitude of the force, multiply the shorter distance. By now, it should be very easy to locate the shorter distance. That's from A to B. That's 2.5. So 20 times 2.5 is the moment of this force at point B. And this moment should be counterclockwise, right? You fix point B and then you rotate. So it's counterclockwise. That's going to be positive. By and Bx are not involved in this equation because they are passing through that point we pick. Okay, let's forget about it. Now we have a 40 kilonewton. So 40 kilonewton times the shorter distance. The shorter distance should be from B to this force line. That's B to C. B to C is 3 meters. And this one should be clockwise, then negative. Okay? Finally, you have dy. So dy times the shorter distance. The shorter distance from B to this force line, so that's from B to D. B to D is 5 meters. And this one should be counterclockwise. That's positive. And no more. That's equal to 0. Okay? So from the third equation, immediately you get dy. The dy, the value of dy is (14 kilonewton). Okay? And this is a positive. That means what you assume is right. It is going up. By plugging dy equal to 14 back to the second equation, this is called the second equation. I typically call the equation 1, the equation 2, and the equation 3, right? After we got dy equal to 14, plugging back to the second equation, then you got by. Okay, so by is 46. And again, never forget the unit. Okay, so that's the first step. Simply calculating all the reactions. We got all these 3 reactions, okay? Any questions? Just simple enough now. Step number 2. Step number 2 is start to select segment by segment. So again, we are trying to virtually traveling from point A. The way I typically do is always from the left all the way to the right. That's the traveling path. So, as I explained to you, there are discontinuity at point A, discontinuity at point B, discontinuity at point C, discontinuity at point D. So among A, B, C, D, you basically have to deal with the 3 segments. So that's why we have a segment AB, segment BC, and a segment CD. So we need to make 3 cuts. Okay? So let's do the first cut. That means picking segment AB first. Okay? So after we're done, then we move to BC, make a cut, and then we move to CD, make another cut. So for segment AB, that's still here, right? So we only want to make 1 cut, but this has to be a very typical cut. You cannot say, I have to cut in the center, or I have to cut between A and B 1/3 or 25% location. No, we're going to make a very general cut. So that means we just cut here. Once we cut here, we're going to use a variable to represent that cut. So you cannot say from A to B, that's totally 2.5 meter, then I make this cut, it has to be from here to the cutting point 1 meter, 1.5 meter, 2 meters. No, we make a general cut so that when we make this cut, the whole structure is split into 2 parts. I'm going to look at the left side. You can look at the right side, it's not a problem, but it's going to have more force involved. So that's why typically I want to start from the left side and I want to look at the left part after I made cut. So here is a cutting point. So then the structure falls into 2 parts. I'm going to just look at one part. Here is point A. This is the cutting point. Cut it. And this is called a general cut. How to describe the general cut? I call it X. This X can be equal to 0, can be equal to 0.1, can be equal to 1 meter, can be equal to 1.3 meters, can be 2 meters, can be 2.5 meters. But this is X. Okay? So when I make this cut X, then I need to follow the sign convention, because when I make the cut, I have the internal shear showing up, and that's called V. In addition, at this cutting point, I have the moment. It's called the internal moment. I typically use M. Okay? At the point A, you have a force here, so don't forget this one, which is 20 kilonewton. Okay? And nothing else. You may say there are a lot of forces on the right side. Well, we cut it and we only look at the left side. So that's why we don't need to worry about the right side. This is what we call the free body diagram for part of the segment AB after we make the cut. So if this is the free body diagram, then what? Then we have 3 equations, because chapter 4 tells us after you plot the free body diagram, you always have 3 equations. So the first equation is by collecting all the forces in x direction equals 0. But for this one, we don't have actual forces. We never have actual force for beam problem. So starting from now, I will never write Fx equal to 0. There's no need. It's a trivial equation. 0 equal to 0. So now, starting from beam problem, I'm going to write 2 remaining equations. One is the equation by collecting all the y direction forces and set equal to 0. Okay? So back to this free body diagram, we just plot. Let's collect all the forces in y direction. You have first 20 force going down, that's negative 20. And you have this v going down, that means negative v, and that's equal to 0. Okay? So from this equation, immediately you get v. That's equal to negative 20 kilonewton. And that's the internal shear force. We calculate it. Second, we have another equation, which is called the moment equation. We want to collect the moment of all forces at a certain point in order to calculate this internal moment called M. Obviously, by collecting the moment equation at the arbitrary point, you can pick any point you like. You can pick point A, you can pick this cutting point, you can pick somewhere in between. In general, it doesn't matter. The easiest way to calculate out M is to pick that point, which is called the cutting point. So now, I'm going to choose the point with a fresh cut here. You can choose point A, you can finally solve the problem. But if you choose point A, then what? This unknown force, V, is involved. You may say we already got it. That's fine. But this is based on the previous equation, assuming we haven't solved the problem yet. So it's better to pick the point to calculate the moment based on this cutting point. So typically, that's the one we use. So we take the moment at the cutting point set equal to 0. So then we want to collect all the moment due to forces at this cutting point. Number 1, we have a force acting on point A, which is a 20. So 20 times the short distance. Can anybody tell me what's the short distance? That's x. It's not 2.5. Okay, so the common mistake people can make is to make a cut between A and B, and then when they are trying to figure out the shorter distance based on this force, they pick 2.5. It's not 2.5. We are cutting here with a general, any point, using an x to represent. So that's x. Now, this is the magnitude of the moment, then the direction of the moment. So we are cutting moment at the cutting point. So this force will have the potential to rotate this part counterclockwise, right? That's positive. Now, second, what is the moment due to this v? Well, this v is going through that point. It doesn't count. That's why I want to pick the cutting point. But you still have another moment. So that moment is counterclockwise, then plus moment, that's equal to 0. Then, from this equation, we got a moment. Moment equal to what? Negative 20x. Any questions? By checking these two solutions in this segment, you see shear force is a constant between segment AB. But the moment is not a constant. You may say, well, later on, for any other questions, is shear always constant? And the answer is no. Sometimes the shear is not constant. So that's why, in general, we still need to make general cut. So that's the first segment. It's not done yet, right? So between any cut from A to B, these two are the solutions. And later on, we need to plot. So we leave those solutions there. Now we need to move to the next one. Step number 3. So step number 3, we need to make another segment. And going back to look at this picture, now we need to cut somewhere between B and C. Okay? So going back to the original structure, we need to deal with segment BC. So write down segment BC. So for segment BC, we need to make another cut. So we cut here. But this is a general cut again. It doesn't mean it has to be exactly at the central point between B and C, okay? I just make a cut in general between B and C. So when you make the cut, the structure is split into 2 parts. And it's up to you which part you want to pick. So now I'm going to pick this left side again, left part again, okay? So make the complete cut, it's separate out. So now I need to plot another free body diagram. So make another cut. So now I'm going to plot the left side. So starting from point A again, and this is the point B. This is the cutting point. Okay? So once we make the cut, again, we need to give a shear force V. We need to give a moment. These are to be determined. In addition, point A, there's a 20 kilonewton here. And don't forget, at point B, there's a reaction. We just calculated the reaction from previous here. That's called the 46, which is By, right? 46. So now I need to write 46 here. Now let me ask you, from A to this cutting point, to make this cutting point general, it's not specific at a certain location, I'm going to continue to call this an X. But this X is the same symbol with the previous X, but they are different. I just use the same symbol. Just like this V. You see here, you use in the first segment you call V, right? The second segment after you make cut, you call V again. But it doesn't mean this V equal to this V. Okay, just a symbol. Because V is a function. But this X is the same thing. This first segment X and my current X I just right here, it's a variable. Don't assume this X is the same thing with this one. So that's why people can make a mistake saying after I make the cut, I need to have this one is not X. This should be like a 2.5 plus X. No, it's a different one. Okay, it's a variable. Okay, so now from this free body diagram again, I need to calculate V and M. So first of all, by collecting all the forces in y direction set equals 0, then what? So then you have a negative 20, negative 46, and then negative V equal to 0. So you get a V right away, negative 66, right? put this one. I'm sorry, right, you're right. So this is going down, this is positive, right, and then negative, okay. That's why it's not consistent with my answer. So put this one to the right, so that's a 26 kilonewton. Okay, let me make sure. Great, yes, okay, so there's the one, thank you. Okay, so this is a V for the segment BC. Also, you need to collect the moment equation. Always select the point at the cutting point. Okay, cutting point here. Now let's collect the moment due to our forces. First of all, you have a force 20 at point A. 20 times what? Times the short distance from this one to here. That's called x again. That's why some students always get confused. Oh, how come it's x? This is different location. Well, this x and my previous x are different. Here and here are different. Okay, because they are variables. So 20x and counterclockwise, positive. Then you have another force acting on point B, which is a 46. 46 need to multiply with a short distance. From here to here. Anybody tell me what's the distance from here to here? Speak loudly. Great. Okay. Okay. So this is the moment due to this By going up. But this one is clockwise. So it's clockwise, negative. Okay? And then you have the moment. Moment is counterclockwise, positive. And that's equals 0. Can you see here? Let me move up. Okay? So now, from this equation, you can get the moment equal to, put this, everything to this one, remain here, to the other one to the left. So 46x minus 46 times 2.5 minus 20x, and that's equal to 26x minus 46 times 2.5. Okay, so this is a moment equation. Okay, any questions? Yes?
V is a positive number, but it's going down. So like, does that influence our final answer in any way?
Well, I'll show you how to represent that. Yes, that is correct, because this time we got the V equal to positive 26. In fact, it's going down, because by sign convention, going down is positive. Yes, it is will be going down. But the first step, we got V is negative 20. In fact, it's going up. Yeah, but I'll show you how to plot at the very end. Okay, so this is the step, right? Now we need to move to the next step, because that's the second segment. We are done with, let's move back to here. We are done with AB and BC. Now, step number 4. Step number 4, we need to make the final segment cut related with CD. Okay, because we already decided we need to make 3 cuts. Minimum number is 3. Okay, so now let's cut here. So when we cut here this time, again, the structure is split into 2 parts. So this time, especially for most problems, the last step, we need to pick the right side. If you pick the left side, there's nothing wrong. You just have more force involved. But when I make this cut again, I'm going to look at the right side with less force involved. So now I need to plot. The right side, that's starting from point D. When I make this cutting point here, so keep in mind, when I look at the right side, by sign convention, this V is going up. And then the moment is clockwise. Okay, if I look at the right side. More importantly, what is this? The distance from point D to the cutting point. So when you make this cut, by what we call the X location, we always count from beginning, from the left, A. So from A to this cutting point, that's called X. But now I'm looking at the cutting point to D. That's going to be the total span minus X. So what's the total? 2.5 plus 3 plus 2, 7.5. So here is 7.5 minus X. So if you want to look at the right side, there's a panel, there's a kind of a compromise you have to deal with. So it's no longer X, it's the total length subtract X, because by definition X is always starting from the left end to the cutting point. So now we are cutting here, we look at the right side, then it's supposed to be the total minus X. Okay, so keep in mind, we are dealing with less forces involved, but on the other hand, the distance is different now. It's a 7.5 minus X. Okay, so this is what they call the free body diagram for the new segment cut. Again, by collecting all the forces in y direction, we are going to have v is going up this time. But I forgot, point D, there's a reaction point D, right? The reaction point D we calculated before was that one, D, 14. dy is 14, so I need to put 14 here. Okay, so this is 14. So v is going up, 14 is going up as well, and that's equal to 0, so that you got v equal to negative 14 kilonewton. That's the first equation we can deal, right? The second equation is to collect the moment equation, and always to select the cutting point. Okay, so we select this cutting point. Now you have a 14 times shorter distance. The shorter distance is 7.5 minus x. And this one should be holding the cutting point is going to be counterclockwise. That's positive. And then v will not be involved because v is going through that cutting point. But you have a moment. By moment, sign convention moment from the previous sign convention, moment is clockwise. But clockwise is treated as negative. So that's negative m. That's equal to 0. Now keep in mind, if you look at the right side, that's moment must be negative. From the second equation, you can get m, which is equal to 14 times 7.5 minus 14, no, positive. No, for this one, yep, negative, right? Or you can write the linear term first, plus 14 times 7.5. Okay, so this is the moment equation. Okay, so we're done, almost. The last step is to plot. We need to plot two diagrams. One is called the shear force diagram, one is called the moment diagram. Okay? So typically what you need to do is to assume this is x. And then the first one is v, and the another one is m. Okay? So one is called the shear diagram, one is called the moment diagram. So depending on how many segments we pick, so we're always starting from point A to point B, point C, point D. So B, C, D. Okay? So now back to the previous step, step number 2. Step number 2, let me just fold this one so that I can show you how we're going to plot. So step number 2, the shear is negative 20, right? Is negative 20 means what? Here is negative 20. That's negative 20. And then for the BC, the result we got is positive 26. So now we need to all the way move up to positive 26. And it's constant. So now you need to make this link. This is called the discontinuity. So from here to here, and then 26. And then the third step, which is here, you got V again, negative 14. So move back to negative 14 here. This. Okay? So I hope you understand. Negative 20, the first segment. Positive 26, second segment. Third segment, negative 14 again. But you need to connect them together like this. So this is what we call the shear diagram. Similarly, you can plot the moment diagram. The moment diagram for the first step. Moment equal to negative 20. Negative 20, this is linear. So then x equal to 0, you're starting from 0. When x equal to 2.5, that's point B. So negative 20 times 2.5, you got 50, right? So that's negative 50. Well, we need to move it down. So this point, and that's linear. Okay? And the second segment, the result for the second segment is 26x minus this one. You plot the straight line, is end up with something going up. Like this. And then for the third one, this one, negative 14 plus this one is linear again. It's back to this. So when you plot a linear function, you need to find out the critical, at least 2 points. Huh?
Can you give the moment one more time?
Okay. The first one, first segment AB. From the result we got, m equal to negative 20. This is a linear function. You need to find out 2 critical points. So pick point A. You pick point B, you plug in this one into here, you got 2 points and make the straight line connection. Similarly for the second one and the third one.